Hello students, welcome to the class on third semester complementary mathematics paper. In the last class, we defined unit tangent vector and unit normal vector of a smooth curve C represented by the vector function r of t. The unit tangent vector is given by vector t is equal to r dash of t divided by norm of r dash of t. And the unit normal vector is given by vector n is equal to t dash of t divided by norm of t dash of t. Here we define another vector which is orthogonal to both t and n. We already know that these two vectors are mutually orthogonal. Now we are going to define another vector which is orthogonal to both t and n. We know that if a and b are two vectors, then the vector a cross b is orthogonal to both a and b. So, the vector defined by vector t cross vector n, that is denoted by vector b, this vector is orthogonal to both t and n. And we know these two are unit vectors. So, vector b is also a unit vector. So, it is called a binormal vector, which is a unit vector. So, the three vectors, vector t, vector n and vector b are unit vectors and they are mutually orthogonal. So, these three vectors form a right-handed set of mutually orthogonal vectors and is called the moving trihedral. We are all familiar with the unit vectors I, j and k, and we know that these three unit vectors are mutually orthogonal, and we know I cross j is equal to k, k cross I is equal to j, j cross k is equal to I. Similarly, for these three vectors t, n and b, we have t cross n is equal to vector b, n cross b is equal to vector t, and b cross t is equal to vector n. Now, if we consider the three space, that means the xyz plane, then there we have xy plane and yz plane and also xz plane. So, here also we have a plane of vector t and n and a plane of vector n and b. Similarly, a plane of vector b and t. Now, these three planes have some special names. The plane of t and n is called the osculating plane, and the plane of n and b is called the normal plane. Similarly, plane of vector t and b is called rectifying plane. Next, let us have an example to find the vectors t, n and b. We are given the position of a moving particle. It is described by this vector function r of t is equal to 2 cos t I plus 2 sin t j plus 3 t k. We have to find the vectors vector t, n and b. Also find the curvature. So, the position of a moving particle is given by r of t is equal to 2 cos t I plus 2 sin t j plus 3 t k. So, in order to find these three vectors, first of all, we have to find the derivative, that is r dash of t. We know r dash of t is equal to, differentiating this, we get 2 into negative sin t I plus 2 cos t j plus 3k, and So norm of r dash of t is equal to square root of 4 sin square t plus 4 cos square t plus 9. Here 4 is a common factor. So this is 4 into sin square t plus cos square t. That is 4 into 1. So we have 4 plus 9. Square root of 4 plus 9. That is root of 13. So norm of r dash of t is equal to root of 13. Now we have the formula. Vector t is equal to r dash of t divided by norm of r dash of t. So it becomes, we have r dash of t is equal to this vector. It is divided by root of 13. So we get negative 2 by 13 sin t I plus 2 by root of 13 cos t j plus 3 by root of 13 k. So this is the vector t. Next, to find vector n, and n is equal to t dash of t divided by norm of t dash of t. So we have t of t is equal to this vector. So differentiating, we get dt by dt, that is equal to minus 2 by root of 13 into derivative of sin t, that is cos t, into vector I, plus 2 by root of 13 into derivative of cos t, that is negative sin t, into vector j, plus here derivative of the last term is equal to 0. So this is the vector dt by dt. Next, consider the modulus of dt by dt. It is equal to square root of 4 by 13 cos square t plus 4 by 13 sin square t. Again 4 by 13 is a common factor. So 4 by 13 into cos square t plus sin square t, that is 1. So we get root of 4 by 13, that is equal to 2 by root of 13. So we have vector n is equal to this t dash divided by 2 by root of 13. So upon division we get minus cos t I minus sin t j. So n is equal to minus cos t I minus sin t j. Next we have to find vector b, and it is equal to vector t cross vector n, and it is equal to, we know a cross b is equal to determinant first row ijk, second row components of vector a, third row components of vector b. So here t cross n is equal to determinant of first row ijk, second row are the components of vector t, that is we have vector t is equal to this. So first entry here is negative 2 by 13, 2 by root of 13 sin t. Then second entry 2 by root of 13 cos t. Third entry 3 by root of 13. Now the third row of this matrix is the components of vector n, that is x component is negative cos t, y component negative sin t, z component is 0. Now expanding this determinant, we get vector I into, we delete the row and column containing I, then we find the determinant of the remaining 2 by 2 matrix. So I into 2 by root of 13 cos t into 0, that is 0 minus 3 by root of 13 into minus sin t. So we get I into positive 3 by root of 13 into sin t minus j into, we delete the row and column containing j, and so determinant of this 2 by 2 matrix. So here negative 2 by root of 13 sin t into 0, that is 0 minus negative cos t into 3 by root of 13. So minus of minus plus. So we have negative j into 3 by root of 13 cos t plus vector k into multiplying, we get 2 by root of 13 sin square t minus of minus, that is plus 2 by root of 13 into cos square t. And here we can take this scalar 2 by root of 13 outside. So simplifying, we get 3 by root of 13 sin t vector I minus 3 by root of 13 cos t vector j plus 2 by root of 13 k. So this is the binormal vector B. Next we have to find the curvature kappa. It is given by the formula norm of t dash of t divided by norm of r dash of t, and it is equal to, we got that norm of t dash of t is equal to 2 by root of 13 divided by norm of r dash of t is equal to root of 13. So it is equal to 2 by 13. We will do one more example. At the point corresponding to t is equal to pi by 2, on the circular helix defined by r of t is equal to 2 cos ti plus 2 sin t j plus 3t k, find an equation of the osculating plane, the normal plane and the rectifying plane. So here we have to find equations of these three planes at t is equal to pi by 2. So we have r of t is equal to 2 cos ti plus 2 sin t j plus 3t k. So whenever t is equal to pi by 2, r of pi by 2 is equal to 2 cos pi by 2, and we know cos pi by 2 is equal to 0. So its x component is 0, and sin 2 sin pi by 2, we know sin pi by 2 is equal to 1. So y component is 2, 3 pi by 2. Z component is 3 pi by 2. So r of pi by 2 is equal to vector 0 to 3 pi by 2. Correspondingly, we have the point order triple 0 to 3 pi by 2. So whenever t is equal to pi by 2, the particle is at the point P whose coordinates are 0 to 3 pi by 2. Now we know that the osculating plane is the plane of vector t and vector n. In order to find equation of osculating plane, we need a vector which is normal to this plane, and we know that vector b is normal to vector t and n. So vector b is normal to the plane of t and n. So at the point t is equal to pi by 2, corresponding normal vector is b of pi by 2, and we know b is equal to t cross n. So b of pi by 2 is equal to t of pi by 2 cross n of pi by 2. Now let us find t of pi by 2 and n of pi by 2. So we have vector t is equal to negative 2 by root 13 sin ti plus 2 by root 13 cos tj plus 3 by root 13 k, and similarly vector n is equal to negative cos ti minus sin tj. We have already found this t and n in the previous example. So t of pi by 2 is equal to, we put t is equal to pi by 2 here. So the second term will be equal to 0, and the first term becomes negative 2 by root of 13 I plus third term is as it is 3 by root of 13 k, and similarly n of pi by 2 is equal to, here in this n of t we put t is equal to pi by 2. So n of pi by 2 is equal to, first term becomes 0, second term becomes minus j. Now so we have b of pi by 2, that is equal to t of pi by 2 cross n of pi by 2. Taking cross product, we have negative 2 by root 13 into I cross negative j. So we get positive 2 by root 13. I cross j is equal to k. So 2 by root of 13 k plus here we have k cross j. is equal to negative I. So this becomes negative into negative positive. So 3 by root of 13I. So this is the vector b of pi by 2, which is a normal vector to the osculating plane at the point P. What is P? P is the point 0 to 3 pi by 2. Now you know the point normal form of the equation of a plane. If the normal vector to the plane is vector n is equal to ai plus bj plus ck, and the Cartesian equation of the plane containing the point P1 x1 y1 z1 is given by a into x minus x1 plus b into y minus y1 plus c into z minus z1 is equal to 0. That is, if we have a point P1 x1 y1 z1 on the plane, and if this n bar is a normal vector to that plane, then the Cartesian equation of the plane is given by a into x minus x1 plus b into y minus y1 plus c into z minus z1 is equal to 0. So here we have the point P. P is the point 0 to 3 pi by 2 and a normal vector to the osculating plane, that is b of pi by 2, that is 3 by root of 13I plus 2 by root of 13k. So by this formula or by this equation, we have the equation of the oscillating plane, that is a into x minus x1. That is the first term. What is a? A is the x component of the normal vector. That is 3 by root of 13 into x minus x1. x1 is equal to 0. Plus b into y minus y1. That is, here b is equal to 0. b is the coefficient of vector j. That is equal to 0. So 0 into y minus y1. This is our point P, 0 to 3 pi by 2. y1 is equal to 2. So 0 into y minus 2 plus c into, c is the z component, that is 2 by root of 13 into z minus z1, that is 3 pi by 2. So simplifying, we get the equation 3x plus 2z is equal to 3 pi. So this is the equation. This is an equation of the osculating plane. So I said this is an equation of the osculating plane because if you choose different points instead of this point, if you choose some other different point and some different normal vectors to that plane, then we will get another equation. So this equation of the plane is not unique, but the plane is unique. So we say an equation of the oscillating plane is 3x plus 2z is equal to 3 pi. Next, we have to find an equation of normal plane. We know the normal plane is the plane of vector n and vector b. And in order to find the equation of this plane, we need a normal vector to this plane. And what is the vector which is orthogonal to vector n and vector b? It is vector t. Vector t is a vector which is orthogonal to vector n and vector b. So a normal vector to this plane, to this normal plane at the point P 0 to 3 pi by 2 is given by t of pi by 2. And we got that t of pi by 2 is equal to negative 2 by root 3 I plus negative 2 by root of 13 I plus 3 by root of 13 k. So here we have x component, that is a. Comparing with this, we have a is equal to negative 2 by root of 13 and this is c. Here b is equal to 0 because there is no term involving vector j. And c is equal to 3 by root of 13. Now we substitute in this equation. So we have x1, y1, z1, that is the point 0 to 3 pi by 2, and A is equal to negative 2 by root of 13, B equal to 0, C equal to 3 by root of 13. So substituting, we get negative 2 by root of 13 into x minus 0 plus 0 into y minus 2 plus 3 by root of 13 into z minus 3 pi by 2, that is equal to 0. Simplifying, we get negative 4x plus 6z is equal to 9 pi. So this is an equation of the normal plane. Next, we have to find an equation of the rectifying plane, that is the plane of vector t and vector b. Here also, we know that vector n is a vector normal to vector t and vector b. So, vector n is normal to the plane containing vector t and vector b. So, at the point p 0 to 3 pi by 2, the corresponding normal vector is n of pi by 2. And we know n of pi by 2 is equal to minus j. So, here a is equal to 0, b is equal to negative 1 and c is equal to 0. So, again substituting in the equation, we get 0 into x minus 0 minus 1 into y minus 2 plus 0 into z minus 3 pi by 2 is equal to 0. And simplifying, we get y is equal to 2. So, this is an equation of the rectifying plane.